Welcome everyone. I'm going to be sharing with you today some of the work that we've now largely completed, looking at rainfall-induced shallow landslides. So this is really going to be an overview of a range of bits of work, papers that have been produced over the last 5 years. So in some respects, it's kind of quick and dirty, but it's also going to hopefully open your minds to some of the opportunities that exist with this type of work and the approaches we've been developing. So the structure for the talk is really just to run through the key questions that motivated us throughout the last 5 years, some of the main findings stemming from those questions, and then a quick summary of the key messages and papers that have come from the work. So I'm sure it'll come as no surprise that rainfall-induced shallow landslides are a very important erosion process in the hill country. I mean, certainly the recent extreme weather has brought that into sharp focus, but I mean, this has been a core element of the STEC program for the last 5 years. So for us, seeing what happened in Hawke's Bay and in Gisborne and elsewhere was very much in line with expectations, I'm afraid, from some of the work we've done and recent papers published about projections connected to extreme weather and the incidence of landsliding and the incidence of erosion associated with that. We're, of course, now well aware of the range of impacts that can stem from these types of extreme weather events that trigger thousands, tens of thousands, even hundreds of thousands of landslides over very large areas. And from the very beginning of the STEC program, there was this strong rationale that we need high resolution information to better target erosion control, reduce sediment delivery to streams from these types of landslides. So that's what's driving this work. In terms of the research questions, there are 4 main ones that I'm going to address today. The first one really goes to the issues of methods that are critical to the acquisition of data for the type of susceptibility modeling that I'm going to talk about. And really, this is us exploring how different types of data can influence the model outcomes output. So whether it's manual collected data versus automatic mapping or event level data versus multi-temporal historic landslide data. Having investigated the data question, the next thing we're really interested in understanding is which factors most influence the spatial occurrence and density of landslides. So that's much more taking the data we have, analyzing that data, and seeing what we can find from that data in terms of the relative influence of spatial rainfall factors as well as landscape factors. With the rapid rollout of LiDAR now, there's real opportunity here to upgrade a lot of the work we're doing, and we've been busily doing that in the last couple of years. So we're interested in understanding to what extent those LiDAR DEMs can improve model predictive performance, and building on the LiDAR, the ability now to actually look at the influence of individual trees and how they affect landslide susceptibility and sediment delivery to streams. But before we get started, we need to consider where the data comes from. And fundamentally, this is about use of high resolution imagery. So this is sub 1 megapixel imagery to capture landslide data. It's not just mapping the features of the whole, but also differentiating landslide source areas, the scars, from the deposits. And over the last 5 years, and including some work prior to this, we've assembled a very large inventory of shallow landslides, spanning it now, I think it's 15 sites, hundreds of thousands of landslides mapped. An example of the distribution of those landslides in terms of their area. This one's from about a 43,000 landslide inventory from the Warrapara. Median scar size is 50 square meters. That's a dark vertical line. The issue you can see here with like the freely available sentinel imagery is 10 megapixel size. That means 100 square meters. Unfortunately, most of the landslide scars are below that pixel size. So if you're going to investigate these processes in detail, and if you want to separate scars and deposits, you do need to use the high resolution imagery. Now, in terms of thinking about some of the outcomes of the work, the first question we really want to look at was, what's the trade-off between manual mapping and automated mapping? Now, automated involves the automated classification of imagery to detect landslides. And in this case, we're using an approach called OBIA, or object-based image analysis. And we wanted to understand what is the effect of using manually mapped data. So this is where somebody manually identifies and maps every single landslide in a study area versus an automated approach. Now, to test that, we actually apply the automated approach with no manual refinement to get that sort of base level of performance. And what we found was, yes, model performance was reduced using the ABIA-based data, but the pattern of susceptibility that resulted in the test areas was reasonably similar. The main trade-off was that we found with the ABIA information is obviously we had an abundance of false positives, and that really shows up here in the data, these distributions comparing red, manual, blue, ABIA. And so in those areas with low susceptibility, we're seeing underestimates using the ABIA data. And that's because there are these false positives and they need to be removed. Now, a hybrid approach, which involves the automated mapping with a manual refinement step, can largely resolve that issue. And so you can benefit from the efficiency of the automated mapping, but also ensuring quality. And that seems to be a good way forward in our view. The other question we investigated is this trade-off between event versus what I call multi-temporal records. Now, multi-temporal refers to mapping the same study area through time, typically over the period of the aerial photo record, which is about 70 years. And that involves quite a lot of work. And that's been done in the past. It's certainly seen in the literature internationally as the preferred source of data for landslide susceptibility modeling. But there are some significant downsides, not least the time and costs involved, but also the fact that often this historic imagery is lower resolution, and there are issues, the interval between images, typically 10 to 20 years, so there's a potential problem around detectability of landslide as they sort of diminish over time and they become less visible. Conversely, event scale data has the problem of the pattern of rainfall influencing the results. So when you're modeling susceptibility, you're interested in the landscape influence on susceptibility. So rainfall, or the pattern of rainfall, can confound your analysis. You need to target the core impact area, really, where the differences in rainfall are potentially much less, whereas over the wider footprint of the storm, the rainfall gradients and intensity gradients are going to be much bigger and are going to have a much more influential effect on the pattern of landsliding. So there are trade-offs. That's the point here. None of this data is ideally fit for purpose, but you need to look at the trade-offs and consider what are the implications. And what we found in a first study of its kind was when you compare model predictive performance using a metric here, what AUC, which I won't go into detail about, but simply to say that one is a perfect classification result, that the comparison between an inventory based on a multi-temporal data versus a combination of event data, so event data being recent event data that we mapped in the last few years, they produce very similar and non-statistically different results. And so in other words, event inventories can form a reasonable and sound basis for modeling landslide susceptibility if collected with a targeted approach to those core impact areas. So that's a key message that differs from what's been reported in the literature. And that's been published years ago. Moving on now to factors that influence susceptibility. This really was about taking the data we have and trying to see what can we learn about which factors are most influential and where landslide is likely to occur. So we trained a model using landslide and non-landslide data with an automated variable selection process. So we are not manually deciding what matters and what doesn't. That's the statistical process. We used weather radar that had been calibrated with gauge data to estimate a bunch of pre-storm rainfall accumulations as well as within storm intensities and how they vary spatially across the study area. That's just one example there. And we've got good model predictive performance, and the model allows us to fit a bunch of coefficients. These are based on standardized variables, and we can compare these values and rank them, and they give us a measure of the relative influence of those variables on the presence or otherwise landslides. So a positive value increases susceptibility, a negative value decreases susceptibility. Now, unsurprisingly, certain factors come through very strongly, which was no surprise to us and shouldn't be a surprise to you. Presence of pasture, for example, increasing susceptibility. Likewise, steeper slopes correspond with increased susceptibility. But what's interesting is just below those landscape factors, we see certain rainfall variables coming through, like the maximum 12-hour rainfall intensity or the 10-day pre-event accumulation, so that 10 days prior to the event and its influence on susceptibility in terms of that antecedent moisture. Conversely, we saw the very sort of strong effect of indigenous forests in reducing susceptibility, but also exotic forests and broadleaf indigenous hardwoods, so mapped from LCB, as having an influence to reduce susceptibility. We also looked at the spatial density of landslides. So we're considering here, how does the pattern of rainfall influence the density of landslides? So that's the number of scales per square kilometre. And so we mapped these across the grid. We then looked at rainfall using those rainfall variables that have been pulled out by the models, so the maximum 12-hour intensity and then total event rainfall. And we binned them into categories which were expressed in relation to the 10-year average occurrence interval. So in other words, what the box plots are showing at the top here is the pastoral areas. Once you're at 25% or more above the maximum 12-hour intensity relative to the 10-year average occurrence interval intensity, and we see this step change in terms of the numbers of landslides. In this case, it's a greater than threefold increase. For mean annual rainfall above 10%, or for a storm total greater than 10% of mean annual rainfall, we also see a step change, will be a smaller one. And perhaps one of the key points to note about this non-linearity is that, particularly for the 12-hour rainfall, that magnitude of change, that 25% or greater increase, is actually around about what the level of intensity increase is projected for late century under sort of the strong highest levels of warming with climate change. So this is a potential outcome we can envisage with that more extreme scenario, or something perhaps a bit less, but it certainly points to the prospect that more intense rainfall is going to see a non-linear increase in terms of the number of landslides that could be produced. It's not like a nice linear ramp up in this case. And that's been published just this year, a few months ago, in a paper in geomorphology. Now, in terms of the application of this information, we're applying this to regions to provide information on landslide susceptibility to help target erosion control. Look, over the last few years, we've produced results for the Horizons region as well as Hawke's Bay. These are based on the national 15-metre DEM. This predates LiDAR. However, with the availability or increasing availability of LiDAR, we're now upgrading these outputs to use LiDAR-derived DEMs. And just using a case study from the Warrappa, we found with the same model, same approach, a significant improvement in terms of predictive accuracy, 72 to 88% threat classification in the Warrappa case study. So to illustrate an output for Gisborne recently produced based on LiDAR combined with the LCB 2018 land covers, 5-metre resolution. We can then show that now where we've converted all forestry land to grass. The reason we do this is to express the inherent susceptibility. So we're trying to remove the rotation effect and to make something, to produce something that's comparable in terms of a like-for-like comparison of pastoral areas as well as forestry areas. If we zoom in, this gives you an idea of that granularity that comes from the LiDAR-based 5-metre resolution output compared to what is presently used, at least in the forestry sector, for assessing susceptibility, and there's erosion susceptibility classification, which is part of the National Environmental Standards for Plantation Forestry. So it just gives you that appreciation of that high resolution information that's now available. Now, moving on to the question of individual trees. This is work that was done by Raphael Spiekermann, who was an employee at Landcare until recently and completed his PhD within the program. Unfortunately, Raphael decided to move back to Europe, but he made a great contribution to the program while he was here. And so I'm going to talk to some of that work just to represent it here at this meeting. Really what this focuses on is using the LiDAR information now to actually go down to the level of individual trees and assess their influence on susceptibility. So the work I showed you earlier was focused on using land cover information, so LCV based, over large areas, regions in particular, but at high resolution. This is now going down much more towards a farm scale focus, down to the scale of individual trees. And so the test area for this is in the Warrappa. It's a study area, it's over 800 square kilometres. We mapped over 43,000 landslides in that area. And if we zoom into a kind of a case study farm, just to sort of illustrate the application of these high resolution methods, we've chosen this farm here. The background here is 5-metre resolution LiDAR DEM based susceptibility modelling. So it's land cover based, just gives an idea of that pattern of susceptibility, red being high, green being low. But we zoom in further now and we can see very clearly the widespread presence of these spaced trees in pastoral areas, in many instances which would be mapped as just pasture in LCB, but which, you know, on closer inspection obviously contain a number of trees. And so the opportunity that LiDAR presents here in this instance was the ability to identify the location of these trees and then to calibrate a model which looked at the influence of trees on slope stability based on the distance from tree. And so what that looks like is illustrated here, where based on the tree type, you can then look at the spatial variation in the what's called the TIMS, the tree influence model on slope stability, which expresses that influence on stability with distance from tree. And so you can integrate that information, which the actual derivation of that's described in this paper by Raphael from 2021, into our modelling for the farm. So this is 1-metre resolution landslide susceptibility, but for a treeless baseline. As you can see, there's extensive areas of high susceptibility. If we add in the present tree cover, there's a notable reduction. It actually equates to about 43% reduction in landslide erosion was estimated based on that shift in susceptibility. And the work underpinning that's also been published last year. Now, as I mentioned at the start, we're interested in not just where landslides occur, but also sediment delivery. And to quantify sediment delivery from landslides, we need a model that predicts where landslides are likely to deliver sediment to streams versus those landslides that occur but are much less likely to deliver sediment to streams. And so to do that, Raphael assembled an inventory from a 1970 storm where we had good imagery and we could map source areas and deposits. And he fitted a statistical connectivity model that looked at a range of factors that might influence the likelihood of a connection spatially to a stream. And so that the model that came from that data set and has now been integrated into this modelling So I'm just returning back to my previous slide. So this is the treeless baseline susceptibility, only 1 meter resolution. What happens if we bring in now a view that's informed by not only where a landslide is likely to occur, but how likely are those landslides to deliver sediment to a stream? And that's what happens when we integrate the two. So now what you can see are areas shaded red that have a high likelihood of landslides occurring and those landslides delivering sediment to streams. And what that does is approximately halves the area that was deemed high susceptibility. So it's a significant refinement if you're interested in planting trees to reduce landsliding, not just the incidence of landsliding, but also the likelihood that those landslides that occur also deliver sediment to streams. So it's about that smarter targeting. And if you actually overlay the tree cover that's present, you can see a further significant reduction in terms of the area that's susceptible. And a key statistic that I pull out from the paper that was published by Raphael last year is that across the 50 farms in the Warrapa study area, there was a 34% reduction in the estimated landslide derived sediment entering streams if you planted 6.5% of that area. So that really illustrates this idea that if you plant trees in the right places, you can get far greater bang for buck. But you need to be smart about where you put those trees in order to maximize not just the reduction in landslide susceptibility, the reduction in the incidence of those landslides delivering sediment to streams. And that's all captured in this paper from 2022. So to sum up, key messages really. What I think we've demonstrated is automated approaches to mapping with manual refinement, and I stress that, can enable rapid acquisition of landslide scar and deposit data, but it requires high resolution imagery to do that. Statistical landslide susceptibility models provide a data-driven approach to better target erosion control, both from the regional scale, and we've now modeled with LiDAR multiple regions, but we've also done it right down to the scale of the individual tree. And so that application of these methods at the farm scale down to the operational decisions of where to plant trees can be informed by these types of approaches. As I've touched on quite strongly, LiDAR is a huge opportunity for these methods. It's enabling new data collection, new approaches, improved model performance, and higher resolution susceptibility maps. We've demonstrated statistical connectivity models can support target erosion control to reduce landslide sediment delivery to streams. So it's really important to be clear-minded that if your priority is to reduce sediment to streams from landslides, then you need to consider this additional question of how likely is that landslide to deliver sediment to a stream. And from our analysis, we've seen that there is the prospect of a large increase in landslide spatial densities with intense rainfall under the highest level of future warming. So that's quite concerning in terms of what we might see in the future, which underscores the need for this rapid and widespread rollout of mitigations to build that sort of landscape resilience. It's been a very productive area, 7 papers. We've really done a lot of work, I'd say, and we've made, in my opinion, a significant international contribution as well as a local one. Some of this work has now been highly cited, and it's been well received internationally. So I think that's a real sort of positive outcome. I would also stress that this work is ongoing. We're actually continuing to develop the connectivity model with work by people like Anatoly Ziplinnikov, who's a new member of staff, who's basically working at expanding that connectivity model using a much larger database of landslide scars and deposits from Northern Hawke's Bay. And we're also continuing to develop the landslide susceptibility models as we acquire more data. So the work continues. We're anticipating a further publication in the next six months or so. But I think we've made a lot of progress, so we're pretty pleased with where we got to on this. So thanks very much for your attention.